Hey everyone, welcome. I'm absolutely thrilled to have you here for this explainer. Today, we're doing a deep, highly structured teardown of the Universal Verification Methodology, UVM. Think of it think of it as building this incredibly synchronized, fully automated factory just for your hardware verification. It's a real game changer. Let's get right into it.
So, here's our blueprint for today. We're going to start with the UVM framework and the UVM Testbench Architecture. From there, we'll hit the verification agents, the UVM execution phases, transaction-level modeling, or TLM, and wrap it up with the UVM configuration database.
Okay, let's dive right into Section 1, the UVM framework. UVM didn't just magically appear out of nowhere, right? It's actually a standardized methodology that evolved over a solid decade. If we trace its roots back to 2001, it started off as the E-reuse methodology, or ERM. That framework really laid the groundwork, and then it evolved into the Open Verification Methodology, OVM, back in 2007. That was actually a joint effort by Cadence and Mentor. And then finally, in 2011, Accelera approved UVM 1.0. This whole evolution was absolutely crucial because it brought this standard, factory-like automation along with a super robust SystemVerilog base class library to the entire electronic design automation industry.
All right, shifting gears a bit to Section 2, the UVM Testbench Architecture.
So this is the actual macro-level blueprint of our verification factory. The UVM Testbench is your top-level module in the hierarchy. This is where the design under test, the DUT, the actual physical hardware you're verifying, gets instantiated right alongside your verification environment. But here's the thing. What makes UVM just incredibly powerful is the UVM test component. This thing is dynamically created at runtime using a factory registration process. So what does that mean for us? It means you literally only have to compile your test bench once, just once. But you can run countless different tests because the UVM test dynamically instantiates the top-level environment, configures the whole shebang, and then applies specific stimulus straight down to the DUT.
Moving right along to Section 3, the verification agents. Let's zoom in from that macro environment down to the specific workers on our assembly line.
Think of the UVM agent kind of like a floor manager that groups together three really essential workers: the sequencer, the driver, and the monitor. The sequencer is basically the dispatcher, right? It manages the execution and flow of your high-level sequence items. Then you have the driver. The driver takes those abstract items and actually translates them into low-level pin signals to drive the DUT interface. Meanwhile, the monitor is sitting there observing. It samples that DUT interface and converts the pin-level responses back into high-level transactions. And then, sitting just outside the agent, we've got the scoreboard. The scoreboard collects these responses and checks them against a reference predictor model, just to make absolutely sure everything is acting exactly how it should.
Now, with all these factory components working together, we need a really strict shift schedule to make sure no worker acts out of turn. That brings us to Section 4, UVM execution phases.
Now, what's really interesting about this setup is the clear distinction between the setup phases and the actual simulation phase itself. Take a look at the time-consuming piece. Setup phases, things like build and connect, and even the ending phases like extract and check, they do not consume simulation time. Zero. They execute in 0 time, setting up and tearing down the topology either top-down or bottom-up. But the run phase, that is the time-consuming phase. It executes in parallel across all components in completely different threads. This is the moment where the actual stimulus is driven into the DUT and the clock actually ticks forward. Because the run phase operates in parallel across all these independent components, they're obviously going to finish their tasks at different speeds. UVM handles this with something called the objection mechanism. So, the crucial point here is, if a component is taking a long time to complete a task, it absolutely must raise an objection at time 0 and then drop it when it's finished. As long as there's at least one objection raised anywhere in the test bench, the simulation stays alive in the run phase. But if no objections are raised, the simulation will instantly bypass the run phase, jump directly to the extract phase at 0 nanoseconds, and your test will effectively do absolutely nothing. It's a classic pull-your-hair-out headache for first-time UVM users, for sure.
Okay, so we've got our workers, and they are all perfectly synchronized on this strict schedule. But let me ask you this. How do all these completely independent components actually talk to each other without creating this chaotic, messy web of hardwired connections? Well, the answer is TLM, or transaction-level modeling. Instead of wiring low-level module ports together like the old days, TLM lets us transfer data at a much higher level of abstraction. We basically pass transactions, which are just structured data objects, using standard method calls between our producer and consumer components. This creates a brilliant plug-and-play reusability. You end up writing way less code, your simulations run significantly faster, and you get to maintain completely independent components. Let's explore the exact mechanics of how this data actually moves in Section 5, Transaction-Level Modeling. Within TLM, data transfers generally fall into two distinct execution semantics: blocking and non-blocking interfaces. A blocking interface conveys transactions in such a way that its methods literally do not return until the transaction is successfully sent or retrieved. Think of blocking kind of like making a phone call, where you're waiting on the line for someone to answer. Because this process can consume simulation time, they are declared as tasks in SystemVerilog. A non-blocking interface, on the other hand, attempts to deliver a transaction immediately without consuming any time at all. It's more like dropping a letter in a mailbox. These are declared as functions, and they can return a failed status if, say, the target is busy and just can't accept the request at that exact moment. To properly route all these method calls, TLM uses a pretty strict taxonomy: ports, exports, and IMPs. Going back to our factory metaphor for a second, a port is your sender. The IMP is the machine doing the actual heavy lifting, and the export, that's just a doorway routing the data through the factory walls. Getting a bit more technical, a port is instantiated by a producer component that's initiating a transaction. An IMP is instantiated by the consumer component, which actually provides the programming implementation of the method. And the export just acts as a middleman. The rule to remember here is that data always flows from the origin port through exports straight down to the destination IMP. Let's look at how this builds the hierarchy step by step. When you're connecting components, you have to follow specific routing rules based on where they set. If they're at the same level, you make a peer-to-peer port-to-export connection. If a child component needs to send data up and out of its parent, you use a port-to-port connection. Now, if a parent receives data and needs to pass it down to a child, that's an export-to-export connection. But ultimately, and this is key, the very last connection in the entire chain must result as an export to AMP, because that's where the actual code implementation lives. And the cool part, UVM resolves all of these hops at the very end of the build phase, which creates this direct, lightning-fast link from port to implementation. And this actually brilliantly illustrates the difference between standard TLM ports and analysis ports. Standard TLM ports are point-to-point. You have one producer communicating with one consumer using put, get, or peek operations. But an analysis port, that is a one-to-many broadcast. It uses a single non-blocking write function. This means a single monitor can connect its analysis port to multiple subscribers, like various scoreboards and coverage collectors, and just blast that transaction out to all of them in the exact same zero-time delta cycle. It keeps everyone perfectly updated without missing a single beat. Finally, we need a way to send global instructions and settings across our entire factory floor. That brings us to our last section, Section 6, the UVM Configuration Database. So data can be shared across the test bench using two main mechanisms. First, there's the UVM_resource_DB. This is a global parameterized container for storing arbitrary data. You can retrieve items by name or type, and it essentially operates like a giant global pool. But layered right on top of that is the UVM_config_DB. This one provides a much simpler, structured interface specifically designed for managing component-level configurations. Because it actually respects the component hierarchy, the config database is the heavily recommended tool for tasks like passing virtual interfaces from the DUT all the way down into your test environment. Passing this configuration data does require some pretty exact scoping, though. Step 1, from a top-level component, you call the static method UVMConfigDBSet. You pass it a context like this or null and a string for the instance name. This tells the system exactly who is allowed to see the data. Step 2, the target component calls UVMConfigDBGet using a matching scope to retrieve it. And step 3, always check the return value. If get returns a 1, boom, you successfully grabbed the resource. If it returns a 0, the data wasn't there. You can even use wildcards in your instance string to instantly configure every single component under a specific subtree, which is just incredibly handy. So let's bring this all together. UVM acts as a highly synchronized, automated factory. We have our macro architecture defining the entire building. We've got our verification agents working the assembly line. A super strict execution phase schedule ensures literally nobody acts out of turn. TLM serves as our high-speed communication network, and the configuration database passes memos seamlessly across the factory floor. The whole thing has a precise schedule and a precise protocol. Which leaves us with this final thought. If the universal verification methodology brings this much incredible automation, structure, and rigor to your test bench, what hidden bugs and bottlenecks are just waiting to be discovered inside your own design under test?
Armed with this framework, you are perfectly equipped to go find out. Thanks for joining me on this explainer, and hey, happy verifying!